Good morning, everybody. I hope this is okay with everybody if we just do it this way. I mean, it'll save everybody time from driving to downtown Dallas. But if you want me to, I can meet you in the classroom anytime you want, or we can meet on Zoom. So let's begin this way. All right, we're going to do section 4 today, the chain rule, which is what we've been doing all along in the first place. And when we do implicit differentiation, we do the same thing. We use a process of the chain rule. Now, what exactly is the chain rule? The chain rule is when you do let's say we had f of x equals sine of 2x. If we're going to find the derivative of this function, what we're really finding is sine u du. So, and in this case, u equals 2x. So what we're doing here is we have a function within a function, and that's exactly what the chain rule builds off of. So to find the derivative of sine u du, or sine 2x, we first find the derivative of the inside. The derivative of 2x is 2, and then we do the derivative, well, then we just write what's on the outside, so it's just sine 2x. So we do the derivative of the inside, write the equation down, and then take the derivative of the inside, the function. Derivative of sine is cosine. So we have 2 sine 2x cosine 2x. Okay. And then we can use the trig identities to rewrite this as a double angle or a half angle. So all those sheets I gave you earlier this week and last week, you will be using those a lot. Okay, so again, what we said is chain rule deals with a function within a function, because that's what we have. We have sine 2x, that's sine of u, so we have this outside and the inside. So, and that's exactly what we're going to be looking at. We'll be using something called a dependency diagram. To show you what's going through this thing. All right, so dependency diagram is simply a diagram that shows you the flow of logic. So in other words, our first, if we did this, we have our function g, it's taken the derivative with respect to t. So that gives us the inside. Then we take our derivative of the outside function with respect to g of t, and that gives us our derivative. All right, so whenever we deal with multiple variable equations, we use w. So just get used to it. Here's the first one with only one variable. So we start with our function. We go take the derivative of our outer function with respect to x. That gives us our value x. And then we take a derivative with respect to t. Because again, it's a function within a function. So what we have here, our dependent variables are here. That's what we start off with. Because remember, w depends on the value of f of x. And that defines our independent variable, which in this case, because it is not our actual independent variable, because x is a function of t. It's called an intermediate variable. And then when we take the derivative of that part, then we get to our independent variable, t. So basically what this is showing us is if we were going to take a derivative of our function with respect to t, and we know that our function is also with respect to x, we first do the derivative with respect to x. That's what we did first. And then we take the derivative of x with respect to t, because x is a function of t. So really what this means is f of x of t. Right, so again, that's in essence, that's what we're looking at for the chain rule. And this is what we've been doing in calculus 1 and beyond for single variables. Let's look at two variables. Remember our diagram earlier starts with our initial function, went to the intermediary, and went to independent. So dependent, intermediary, and then independent. Because we only had one variable, we go straight down one line. When we have two variables, we'll now take two paths. And then from there, we'll end up with our t. So depending on how many variables you have, that's how many paths you have. This is w f of x, y. So this is with respect to x of t. This is with respect with y of t, because they're both, the function is both x and y. And then we'll go to our favorite value t. So we have a theorem here that defines this stuff. The chain rule for functions of one variable one or two variables, or higher actually, defines as this. If our composite function w equals f of x, y is continuous and differentiable at all points inside the domain, and we have a couple more ifs now, and if x is a subfunction of t and y is a subfunction of t, are also continuous and differentiable on the domain. Remember, what this says is since our functions are like this, x of t, y of t, t has to be in the domain. Then the composition of x and y becomes w f of x t y of t. Is continuous and differentiable. So basically working inside out. If our sub functions x of t, y sub t are continuous and differentiable, and they're part of the composition of our function f or w, then since those are continuous, the function is continuous, and therefore the whole thing is differentiable. Now, since w is a function of f, and which is a function of t, when we write our definition, we have to write it with respect to the lowest variable in the function. So when we do this, we're looking at with respect to t. So that means we have two parts. We have our function. So we take it with respect, first off, we take it with respect to x. And then now, remember, this is chain rule. So since we took the derivative of the outside, now we take the derivative of the inside. So we take the derivative of x of t. So that's just the x part. We'll do the same thing with the y. Take the derivative of the overall function times the derivative of the subfunction with respect to y. So that is how the chain rule works. Well, actually, we're taking w with respect to t. What this says is we take the partial derivative of the first one with respect to, since we did the x, times the derivative of x, which is a function of t. That's what that says. This one is a partial with respect to y. And then the y with respect to t. All right, so that's pretty much what it's looking like. And it grows up even further. So if we had z, we have a plus partial of w over z, zt. So now we can look at this as our diagram. We start off with our function. We have the x part and the y part. Remember, these are dependent variables. We go to our intermediary. So what we do here, this is where we do the partial with the first parts. So that now finds us our x and our y. Remember, these are functions with respect to t. So now we take our derivative dx dt, end up with t, and this side dy dt. All right, so it's pretty straightforward. I mean, actually, if you read the chapter, it looks more complicated than it really is. It's just doing the chain rule, which we've done from Calculus 1. Let's look at an example here. Use a chain rule to find the derivative of that. With respect to t along the path, x is cosine t and y is sine t. So what we have to do first, remember, to find the derivative of dt, we have two parts. The partial of w with respect to x then the derivative of x with respect to t, and then the partial of the original function with respect to y, then dy dt. So we have to find the derivatives of both of these. X equals cosine t, y equals sine t. The derivative of cosine is negative sine. The derivative of sine is cosine. Now, we take the derivative of our entire function here. Derivative with respect to t. We'll first take the derivative of x. That means take the derivative of x, which is 1, and leave y alone. So this is the derivative of x, leave y alone. Then the next part is take the derivative of y, leave x alone. Now we can start plugging stuff in there. X prime is negative sine t. Y is sine t. Y prime is cosine t. X is cosine t. Negative sine squared t plus cosine squared t. Okay, and this is exactly what we did with the chain rule. So we have this times this plus this times this, which is exactly what that says. Now, we could stop there saying that this is our derivative, but looking at our sheet of the trigonometric identities, we could simplify this as saying it's cosine double angle. All right, so you have to keep that sheet next to you so you could keep on referring to this. So, all right. All right, there's a theorem now for 3 variables. This is the chain rule for 3 variables. All right, so if we have a function w is made up of x, y, and z, is continuous and differentiable at, on the domain, and x, y, and z are differentiable functions with respect to t. In other words, we have x sub t, y sub t, and z sub t. Since those are continuous and differentiable, and they're parts of the function w, then w equals the function is continuous and differentiable. again, it looks exactly the same way. Now that we have three variables, we have our function w. Because remember, what this thing looks like is f of x of t, y of t, and z of t. So since we're taking a derivative of w, it has to be with the innermost variable. So what that means is our first one, we take a partial of w with respect to x, then x with respect to t. Then we take a partial with respect to y, then take the derivative of y with respect to t. And then lastly, with respect to z, times the derivative of the subfunction z of t. Again, since we have three variables, the diagram's going to look just like that. So we start off with our function. This is w with respect to x, w with respect to y, and w with respect to z. So this gives us x of t. This gives us y of t. And this gives us z of t. Then take the other half. This is the derivative of x with respect to t, the derivative of y with respect to t, and the derivative of z with respect to t. Okay, some of you may be confused. How do you read this? Well, let's look at this first part. Since we're dealing with x, so I'm starting with a function. I'm taking partial of w with respect to x. Oops, that should be x. So I took the partial with respect to x, and then the derivative of x with respect to t. That's the first path. Now I add this path. W with respect to y times y with respect to t. Then we have to add the last path. Partial with z and derivative of z with t. So we separate each possible path, and then we add them all together at the end. So this is our first one, that's our second one, and this is our third one. All right, let's look at an example here. W equals xy plus c. Yeah, if you want to, you can go ahead and plug in the variables in there if you want. So you could do it both ways. You could, since x is cosine t, y is sine t, and z is t, you can go ahead and do it that way. So we have to do here, since we have a product rule, we have the x and y, and then the derivatives of x and y. Since it's multiplication, I add them. So it's y times x prime plus x times y prime plus z prime. So what we have to do now anyway is we have to find the derivatives. Derivative of cosine is negative sine. Derivative of sine is cosine. Derivative of t is 1. So right here we have cosine times negative sine. No, y is sine times negative sine. Sine t times negative sine t. x times y prime, which is cosine t plus z prime is 1. Negative sine squared t plus cosine squared t plus 1. Again, we could have done exactly the same thing here. Oh, in our chart, again, if we didn't have computers, I would have just taken this as a firm answer, but this is the same thing as cosine 2t or 1 plus cosine 2t, either one. So, and we could have done the same thing here. We could take a derivative of this one, leave that one alone, plus leave that one alone, derivative of that one, and derivative of t. So you see, we just jump in there. Whatever's easiest for you. But now, what is the derivative's value at t equals 0? What is the derivative's value when t equals 0? 2 times 0 is 0. Cosine of 0 is 1. Derivative is 2. Again, remember, what does the derivative tell us? It tells us the, oh, there's this question. It tells us the slope. Oh, yes, definitely. Okay. So let's say that our function, let's go for 3. Let's say we have 3 variables, x, y, and z. Because what we have to do is, in short, is we have to take the derivative of the first one, leave the other ones alone, take the derivative of the second one, leave the other 2 alone. So we're going to have 3 different functions that we have to do. What the diagram does is it tells us, okay, and the first thing we do, let's take a function with respect to x. So we're taking the partial with our first variable. That gives us some value x, some function x. Because remember, these are all subfunctions with respect to t. So we have functions within functions. So we first have to take the derivative of the, with respect to the outer function. And then we take a derivative with what's on the inside. So take the derivative of dx dt. And that leaves us to our final value. Because whatever we said, like in our last example, what is the function when t equals 0? So this is what we get to, is whatever our only variable we'll have left is t. All right. Then we have to do the second one. We have to take a derivative of the function with respect to y. That isolates the y function. Because now I go from there and I take a derivative of y with respect to t. So I take the derivative of the outermost function with respect to y. Then I do the inside. Likewise on the last variable. I'm looking at it only at z. That gives me z at t. Now I take the derivative of z with respect to t, And what that does is if I add these three paths, this plus this plus this, I get the chain rule. So dz dt, the answer is the partial of the function with respect to x times dx dt plus the partial of the function with respect to y times dy dt. And lastly, the partial with respect to z times dz dt. So let's say we had this function. Where x equals cosine t. But remember, x, y, and z are all functions with respect to t. So y equals sine of t, and z equals, let's say, t squared. Because remember, it's a function of t. We'll do this, I'll do this two ways. I'll first use this shortcut method where I just plug in the values. And then I'll plug in the values first, cosine, sine t squared, and then we'll work out the derivative that way. And you'll find out, you'll see that we get the same answer both ways. So what we have to do first is we have to find the derivative of x, y, and z. So the derivative of x is negative sine. The derivative of y, derivative of sine is cosine. And the derivative of z is 2t. So right here, we have x times y. We're taking the derivative of this small piece here. Because when we have a product rule here, we take the derivative of x and y, and I can use the fishy symbol because I start with the y times the derivative of the first one, x. Since it's multiplication, I add. Then x times y prime. And I do the same thing with this one. My functions are y and z. So y prime, z prime. Since it's a product rule, I add them. Z times y prime plus y times z prime. And then the last one is the derivative of 2x, which is just 2. Now, at this point, all I do is I come over here, x prime, y prime, and plug them in. Y is sine t. X prime is negative sine t. Plus x is cosine. Y prime is cosine. So these four equals this. There's the plus. Now we do z, which is t squared, times y prime, cosine t, plus y, which is sine t, times z prime, 2t. So these four equals this. There's that plus 2. Sine times negative sine is negative sine squared t. Cosine cosine is cosine squared t. T squared cosine t plus 2t sine t plus 2. And the only thing really we could simplify by using the properties was that negative sine t plus cosine t is cosine 2t, and leave everything else alone. And there's the derivative pretty much of our w function. So that it's the diagram just tells us what we do. We have our function, we have our 3 variables, so we have to take the function with the derivative of each variable, and then we have to take the derivative of each variable, and then combine them. And that's what it tells us. So the product here puts together our formula. All right. I hope that helped. All right. Let's look at functions defined on surfaces. Okay. Pretty much, it's going to be the same thing in that, except now, since we're dealing with surfaces, we have to have 2 variables. You can't just have a single surface. So with this, we're looking at here, or we'll have 2 independent variables and 3 intermediate. Because in order to have a surface, you have to have length and a width. So you have to have at least, well, you have to, if you have more than that, then you have a volume. The theorem there says this. If W is a function, composite function with 3 variables, and the surface can be defined by G, H, and R. So we have W is a function of 3 variables, X, Y, and Z. And they're subdivided into these. Remember, we're talking about surfaces. So each surface has to have 2 dimensions. If all 4 of these functions are continuous and differentiable, then the function W has a partial derivative with respect to R and S. Because the function W is at this. And since this function, f function x, y, and z equals g of this, h of that, and z of that, that means W has to be the partial of that, of the R and S, which are the n variables of the function. Now, R and S are different values, are different dimensions. So when we do partial derivative of W of R, then we can also do one of S. So each one of these have an R, and they all come from X, Y, and Z. They all have an S, and all those have X, Y, and Z. So the partial with respect to R is the partial of W with respect to X and dx with respect to R. The partial of W with respect to Y, then dy with respect to R. Partial with respect to Z, and then dz dr. Now, likewise, take a partial of W with respect to S. That means each one of these are functions of X, or S. So I'm going to take it with respect to X. X is a function of S. Partial with respect to Y, and Y is a function of S. And the partial with respect to Z, and Z is a function of S. And each of these have their own diagrams. Okay, you're welcome. Okay, we do the same thing for both of these. So for this first one and the second one, let's do their own diagrams. We're starting off with our function, W. So W, we're going to go with R. So the first one, this one says that we have 3 paths. So this is the partial of W with respect to X, partial of W with respect to Y, and partial of W with respect to Z. Okay, what those end up now, X with respect to R, Y with respect to R, and Z with respect to R. So now we take the second derivative, or the second phase, I should say, second part. Now we take a derivative of X with respect to R, take a derivative of Y with respect to R, and derivative of Z with respect to R. That gives us now our only variable left in our function will be R. Again, this times this, that's the first one. This times this, that's the second one. This times this, that's the third one. So we do the same thing with the last one. We have partial of W with respect to X. This gives us X of S. Partial of W with respect to Y, which gives us Y of S. And the partial of W with respect to Z, which gives us Z of S. Now we take a derivative of X with respect to S, of Y with respect to S, and Z with respect to S. And that's pretty much how you read it and interpret it and draw it. All right, let's look at an example. Express partial W with respect to R and partial of W with respect to S in terms of R and S. So the first thing we have to do, remember, we have W, R, and S. So we have X, Y, and Z and R and S. So our formula, we take R first. Let's take this function with respect to X. So we did function with respect. Now let's take a derivative of X with respect to R. The partial with respect to Y. And since Y is a function of R, we can do that. And lastly, we take a partial of the function with respect to Z, and then take the derivative of dz with respect to R. All right, so W with respect to X is 1. W with respect to Y is 2. W with respect to Z is 2Z. So that's the first part. That's these parts. Now we take the derivative of X with respect to R. So the derivative of X with respect to R is, that's 1 over S is a constant. So it's 1 over S. Derivative of Y with respect to R is just 2R. And then Z with respect to R, which is 2. So we have 1 over S. 2 times 2 is 4R. Oh, that's, yeah, 2Z. We have 4Z. But what is Z? That. Well, 2Z is R times 2. Remember, Z is 2R. So 2 times 2R is 4R. Okay, combine like terms. We got 4R plus 8R equals 1 over S plus 12R. That's the partial of W with respect to R. Now we do the same thing with respect to S. Which is going to be partial with respect to X, dx, ds, partial with respect to y, dy ds, partial with respect to z, dz ds. Remember, the functions are x is equal to r over s, y is r squared but ln s, and z is 2r. And w is x plus 2y plus z squared. So the derivative with respect to x is 1. The derivative with respect to y is 2. Derivative of w with respect to y. And derivative with respect to z is 2z. Now we got to take the derivatives of these with respect to s. So this one, the derivative of s is -1, which makes it negative r over s squared. And we'll fix this in a second. Derivative of y with respect to s, that's a constant, disappears. So derivative of ln s is 1 over s. Derivative of 2r with respect to s is 0. It's a constant. The first one is r, negative r over s plus 2 over s. So that's my partial with respect to s. So again, it's just taking each one of these, look at the w, only worry about this function here with respect to x, with respect to y, so z. Everything else is constant. If you're taking derivative of x, y, and z are constant. Let's look at another example here. There's the diagram. Express partial w over partial r and partial w over partial s in terms of r and s. Partial of r, partial s. We only have two variables, so it's partial of w over partial of x, dx, dr, because that's what I'm looking for. The next one is partial of w, partial of y, that's the second variable, dy, dr. Okay, here's something that's going to be confusing. At least mine, with me, these partials might look like 2's, and I will always get confused or mix them up with 2's if I have 2's in the function. So be very, very, very careful when you do that. So the derivative of the function w with respect to x is 2x. Y disappears, it's constant. The derivative of the function w with respect to y is 2y. Now the derivative of x with respect to r, since r is r, it's equals 1. And y with respect to r, it also equals 1. So what do we have here? We have 2x plus 2y. The instruction says in terms of R and S only. So what is X? 2x is R minus S. Y is R plus S. Two R plus 2R is 4R, negative 2 plus 2. So the partial of W with respect to R is that. Partial of W with respect to S. So partial of W with respect to X, dx, ds, partial with Y, dy, ds. So the first one, this function with respect to X, which is 2x, this function with respect to Y is 2y. Now, X, the function X with respect to S, so R is a constant, disappears, so it's minus 1, dy ds, so it's just positive 1. So it's negative 2x plus 2y. Again, they went in terms of R and S only, so X is R minus S, and Y is R plus S. Negative 2R plus 2S plus 2R plus 2S. 2R's cancel, so we have 4S. So again, it's straightforward. If you just would follow the instructions here and just do each one of those and plug and play, it's just straightforward. All right. Implicit differentiations. Here's a theorem, actually. Suppose the function f x y is continuous and differentiable, which is kind of redundant. I shouldn't do that, because if it's differentiable, it's automatically continuous. And then the function, set it equals 0, f of xy equals 0, defines y as a differentiable function of x. So at any point where f of y does not equal 0, remember this condition is f of y equals 0. If it's not equal 0, then we have the formula the derivative is the partial of the function with respect to x over the partial with respect to y. Let's take an example here. Right. Theorem 8 is what we just said. Find dy dx if x squared minus y squared minus sine xy equals 0. Remember saying that f of xy equals 0. So we have to find, using theorem 8, to find dy dx, we find negative f of x over f of y. So the partial of this function, this is our f right here. The derivative of the function with respect to x, that's a constant, disappears. So it's negative 2x. Remember, this negative stays out in front. Minus sine xy. Take the derivative of the inside, which is y. Leave the function alone. Times the derivative of the outside, which is cosine xy. And divide by no. Derivative of the inside times the derivative of the outside, which is cosine xy. All right. This is sine u. The derivative of sine u is u du. Right. And the same thing with respect to y. Derivative of y is 2y. The x is constant, minus derivative of xy is x times the derivative of the outside is cosine xy. Two x plus y cosine xy, 2y x cosine xy. That's your solution. And then if it gives you a point, it's at the point pi over 2 radical 3 pi over 2, find the value. Let's look at another example here. With 3 variables. Again, it doesn't matter. We do partial derivatives. It doesn't matter how many variables you have. You just repeat the same process. And the diagram, you just have a different, another arm put to it. Find dz dx partial dz dy. So our function is equal to x cubed z squared y e to the xz plus z cosine y. So f of x, since we have 3 variables, we have to find f of x, f of y, f of z. So with respect to x, We got 3x squared. That goes to 0. So the derivative of the exponent is z. So we have yz e to the power xz. There's no x there, so it disappears. It's a constant. Derivative of y. No y there, no y there. The derivative of y is, that goes to 1, so we just have xz. And there's y. The constant, leave it alone. Derivative of cosine is negative sine. Y. And with respect to z, that disappears. That becomes 2z. Derivative of x times z, z disappears, so it's just xy e xz. Derivative of z is 1, so it's cosine y. It's asking us for dz dx. And then for dz dy. Here are partials. So we're looking at negative f of x over f of z. This is going to give us f of y over f of z. Partial, I should say, not f of. So the whatever's on the bottom goes on top, whatever's on is what you're taking a derivative of. So the negative 3x squared plus yz e to the xz over 2z xy yz plus cosine y. So that's the partial. The partial of dz dy is equal to, of course I could distribute that negative in there. So f of y is e xz minus z sine y over z. All right, so that's the first part. We found dz dx, the partial dy dz dy at 0, 0, 0. So at 0, 0, 0. So dz dx. So x, y, and z are all 0. So that becomes 0. That becomes 0. That becomes 0. That becomes 0. And that becomes 1. So we have 0 over 1, which is 0. dz dy on the top, that becomes 1. But 0 is 0, 0, e to 0 is 1. 0 times sine, so it's just 1, negative 1 minus 0. That's 0, and that's 1. So it equals negative 1. And there's those, that's what you're looking at. All right, I hope that helped. Again, I'm working as hard as fast as I can to get everything out to you ASAP, the notes, the videos, putting together the solution videos as we speak. So I'll try to have everything out today, as well as the next section video out too, because I keep on forgetting that there's so many in this section. All right, I hope you all enjoyed it. I hope it was informative. Again, this section hopefully is just plug and play. Okay, everybody, have a great day.